In this video, we will apply everything we have learned about polynomials to find the equation of a polynomial function given its graph. We will use the relationship between the zeros and factors of a polynomial, the multiplicity of zeros, and the end behavior of a polynomial to verify we have found the equation of a polynomial given its graph. So determine a formula for the polynomial p of degree 6 that satisfies p of 0 equals 1/2 and p has the graph below. Assume all zeros of p are shown in the figure. So that means all the x-intercepts that p has are the ones we see on the graph. So there's an x-intercept at -5, -1, and 4. So we know that the corresponding factors for p of x are going to be x plus 5, x plus 1, and x minus 4. That way, if we let x equal -5, we would get 0. Or if x equals -1, this factor would give us 0. And if x equals 4, x minus 4 would give us 0. Next, we want to consider the multiplicity of each of these zeros. So at -5, the graph looks pretty linear as it passes through. So it would probably be safe to assume that that is multiplicity 1 for the factor x plus 5. X equals -1. The graph bounces off, kind of looks quadratic. So we'll start out with a multiplicity 2. If we have to up that in order to get this degree 6, we can do that in a minute, but we'll start out with just the multiplicity of 2. And then at x equals 4, the graph passes through the x-axis, but it looks kind of like a cubic function. It's flatter there, so we'll start out with multiplicity 3. And then if we add up our multiplicities, 1 plus 2 plus 3, that gives us degree 6. So we have a degree 6 polynomial. We have all the factors that correspond to the x-intercepts on the graph. The only thing we need to do now is verify or figure out how we're going to make the graph go through 0, -1. I'm sorry, 0, 1/2. So right now, as is, if you were to let x equals 0, you would not get 1/2 actually. You'd get something much, much, much larger. So what we're going to do is try to find that a value that would either stretch or compress the graph. And one thing we can note here is that because both ends go down, if we were to zoom out, this graph is going to look like negative x squared. And the key here is to think about the fact that that leading coefficient is going to be negative. So when everything's all said and done, this leading coefficient a should turn out to be negative. All right, so we're going to find a by using the fact that we know when x is 0, the output should be 1/2. So we'll say 1/2 equals a times 0 plus 5 to the first times 0 plus 1 squared times 0 minus 4 to the third. And we'll reduce here. We'll have 5 times 1 squared, which is 1, and then -4 cubed. So 1/2 equals a times 5 times 1 is 5. -4 cubed is a -64. So then we have 1/2 a equals 5 times -64 is -320 times a. And then we could divide by -320. I see a fraction over on the other side, so I'm going to actually multiply by the reciprocal of -320 on both sides. And then I see that a equals -1/640. So the good news is we knew that that leading coefficient needed to be negative because of the long-range behavior of the graph, and the a value we found is in fact negative. So our last thing here would just be to put it all together. This polynomial that's graphed must be equal to 1 over 640 times x plus 5 to the first times x plus 1 squared times x minus 4 cubed.